So our first talk today is from Stephen Macke, and he's going to be talking about lineage, fine-grained lineage in Jupyter notebooks, so we can have safer code and not get lost in state and forget about state that's not there, right? So he's currently a PhD student at UC, interested in improving user workflows for machine learning and data analytics, and especially bringing in some of the ideas from the database community. So Stephen, take it away.
Thanks so much, Brian, for that nice introduction. So I'm delighted to come to the central time zone again, this time from the West Coast. So even though I'm a student at UIUC, I've been visiting UC Berkeley. So I'm going to talk about NBSafety, which is a drop-in replacement for Jupyter's Python 3 kernel. The goal is to make it easier to reason about out-of-order execution in computational notebooks. And actually, I just remembered that I have this talk recorded. So I'm going to go ahead and just play that for you all. Should be a bit smoother. Starting now. To first motivate why it's worth the effort to spend time improving notebooks, let's first briefly recap some advantages offered by a notebook programming environment. And since Jupyter in particular has become super popular and has won all kinds of awards and accolades, we'll focus on it during this talk. First, when prototyping ideas, notebooks allow you to incrementally refine code in a cell and rerun it until it's correct, keeping intermediate state in memory the whole time, unlike IDEs where it's hard to observe the effect of your changes without a bunch of extra steps. Next, by allowing users to mix rich text documentation with code, notebooks offer a great medium for presenting experimental results and for providing tutorial-style documentation. And finally, the ability to generate plots inline and tweak their presentation without losing progress is a true game changer. That said, the key advantage of Jupyter and other notebook environments, which is their ability to keep intermediate state in memory and at the ready, can also make them hard to reason about, since this intermediate state is global, hidden, and accumulating over time, and as a result is really hard to keep track of manually. To illustrate this difficulty, let's just consider a simple example notebook where we have 3 cells. We first define a function, call it, then print the result. If I change the function definition, but forget to rerun the middle cell before running the print statement at the bottom, I get a stale result from my output because the Y that was printed depends on a call to an old version of F. And while this example is a bit contrived since the 3 cells are right next to each other, keep in mind that notebooks can become quite large and unwieldy, and it's not uncommon to have these kinds of dependency chains spread out over time and space. Keeping track of how how cells depend on each other is thus a burden shouldered by users who might end up making mistakes that actually can be really subtle, so they might not even realize sometimes that there's an error. This has prompted some backlash against results presented by a notebook medium in the Twitter sphere, with folks saying things like restart and run all, or it didn't happen. It seems as though there's a safety interactivity dichotomy where if we allow ourselves the interactive benefits of going back, editing cells, and running them out of order, we give up on safety and increase the likelihood of errors. While if we force ourselves to be really disciplined about running each cell exactly once and in order, we can be more confident about our results, but give up a lot of those interactivity benefits. As a result, my collaborators and I developed NBSafety to address some of these concerns. To illustrate it, let's look at how NBSafety behaves for that same simple example from before. Recall that I have 3 cells. I define a function, call it, then print the result. Using the NBSafety kernel, if I change the function definition in the first cell from x+2 to x+3, NBSafety gives me 2 kinds of highlights. First, the last cell gets a stale highlight because Y depends on a call to a previous version of F. To refresh the staleness in Y, NBSafety recommends that I rerun the middle cell by showing this refresher highlight. If I take the suggestion and rerun the middle cell, now the stale highlight shifts to the output of the last cell, and to refresh the stale output, NBSafety suggests me to rerun the last cell. When I do so, I get an output that's semantically correct given the implicit dependency structure between these 3 cells. Let's take a look at under the hood at how NBSafety accomplishes its magic. NBSafety uses a runtime tracer to build the implicit dependencies between symbols appearing in the cells, and then it uses a program checker to alert users of cells that are unsafe due to staleness, as well as cells that can resolve staleness. Let's look at how the NBSafety kernel instruments a single end-to-end cell execution as depicted in this diagram. The first step is user submits to the kernel a cell for execution. During cell execution, the tracer looks at each statement as it runs and builds up lineage or data flow dependencies between symbols appearing in the executed statements. Here's a quick example of the tracer. In the cell on the right, the first statement that executes assigns 42 to symbol A. So when it executes, the tracer sets symbol A as having no dependencies. The next statement that executes assigns to X a list containing 2 constants as well as the symbol A. And since A appears in the U symbols on the right-hand side of this assignment, NBSafety marks X as having dependency on A. And we also have a bunch of other rules for ascribing lineage or other types or data flow for other types of statements, such as aug assigns, function definitions, class definitions, and others. And I also want to mention that this lineage is only computed for statements that are on the actual path of execution. So the untaken branch of an if statement will not induce any lineage metadata. So that was a quick example of the tracer. Let's look at how the checker then takes metadata from the tracer and identifies staleness issues, as well as staleness fixes. To illustrate the checker, let's look at another quick example. Suppose the symbol foobar is stale in this cell. That is a dependency of foobar changed, and foobar has not yet been updated to reflect the change. To detect that this cell is unsafe, NBSafety performs liveness analysis to compute symbols that are live with respect to the beginning of the cell. In this case, there are 2 such symbols. Symbol num, whose value before cell execution is used right away, as well as foobar, whose value before execution, which recall is stale, could be used in this print statement at the bottom if either of the branches here or here in the if statement are taken. So that was how we use liveness analysis in conjunction with runtime lineage metadata from the tracer to detect stale usages. How does NBSafety determine staleness fixes? One strategy could be to determine whether concatenating pairs of cells removes live references to stale symbols. For example, suppose symbol Y is stale in the simple notebook depicted. Y is clearly live if we restrict our attention to the last cell, but if we append it to the cell before it, Y is no longer live at the top of these joined cells because it is immediately killed in this assignment here. This is exactly what we need to determine that the middle cell is a refresher for the stale usage in the bottom cell. Unfortunately, this method of computing staleness fixes or refresher cells requires us to run liveness analyses on all pairs of 2 cells concatenated together. And this does not scale for large notebooks. It's kind of quadratic complexity. Instead, we make use of another analysis technique called initialized variable analysis or definitely defined analysis. If we go back to our previous example, this analysis would tell us that symbol S is definitely defined by the time we reach the end of this cell, because it is assigned in every branch of the if statement in this cell. So if S were stale, initialized variable analysis would tell us that we could run this cell to resolve any stale usage of it. The same cannot be said for symbols foobar or foo if they were stale, since they are each only defined in one branch of the if statement. And so if either of them were stale, the staleness could potentially linger on after we run this cell. This initialized variable analysis only needs to be run once for each cell in a notebook. So we no longer have that quadratic complexity if we were to use liveness analysis on its own for computing refresher cells, that is. So finally, we already saw how the front end leverages these analyses to present cell highlights to the user that alert them of both staleness issues and staleness fixes using those highlights from before. So in the interest of time, I'm not going to go into too much detail on our empirical study, but in short, we scraped 666 real Jupyter execution logs from GitHub that contain richer interaction metadata than what is available from static notebook snapshots alone. And we found that NBSafety's suggestions correlated well with real user behavior. The y-axis of this chart just shows the likelihood users picked different kinds of cells. So in particular, this chart shows how likely NBSafety and users were to arrive at the same choice for what to execute next, independent of each other. In particular, refresher and newly refresher cells were very likely to actually be cells that users chose for execution. So they kind of agree with the choices suggested by NBSafety for what to execute next. The other cells that users were likely to pick for execution next were fresh cells, cells with live references to newly updated symbols, as well as newly fresh cells. So cells that just recently contain live references to updated symbols. So NBSafety also suggests these kinds of cells for execution. And these were much more likely than other kinds of baseline cell types to be picked by real users, even though the users weren't influenced by the choices of NBSafety. On the other hand, stale cells were unlikely to be cells that users chose for execution. And when we looked at particular examples of sessions with stale executions, we found that oftentimes users seemed to be confused and would do things like execute the same set of cells over and over, as if they were wondering why they weren't getting the output they were expecting to see. That concludes this presentation. So be sure to check out nbsafety.org if you'd like to try out our stuff. It's a one-liner for installation, and we of course appreciate any feedback, GitHub stars, and so on. Thanks very much for your attention, and I'm now delighted to open the floor to any questions during the breakout session happening next. Thanks very much.
Hey, thank you very much, Stephen. So if you have questions, you can either drop them in the chat and or raise your hand and then you can throw them at Stephen.
Thank you very much.
So I had a question right away. At the end there, you mentioned that users seem to be stuck, like they didn't understand why things weren't changing. Do you have a sense, is that because they should have been rerunning some of these stale cells that they just didn't touch? Or is that just is that a hypothesis? Or
Oh, okay. So let's go back to that example, which I think is sort of representative of what was going on. So yeah, if we look at this example here, the user might, for example, change. Actually, we'll look at it with the NBSafety semantics, since it's easier to see what's going on. So like, let's suppose the user changed the top cell here. Then they might rerun the bottom cell and be confused when it doesn't change from 4 to 5. So they see 4 again. So then what we would see is they would jump back up to the top cell, try running it again, and jump to the bottom cell, run it again. And they would do this several times. And this is, of course, not this particular example never happened. It's just representative of the types of confusion that we saw when we were looking at these execution logs.
So you haven't been able to put NBSafety in front of people yet to see if it helps their confusion.
So we have not performed a user study, if that's what you're asking, which we would like to do at some point. It is actually available for anybody to use though right now. And I don't know if I should mention this since this talk is being recorded, but I actually used it when I was generating the plots for this work, and one of them maybe would have been wrong if I hadn't been using it. So
that's good. At least a good initial validation.
Sure.
Jeffrey has a question. I can read it out. He says, "I'm curious why you require users to manually rerun stale cells instead of automatically keeping all the cells reactively updating."
Yeah, that's a good question. So I guess I probably shouldn't try and do this live over the air, but there could be cases where there's multiple choices for what to execute. So let's suppose I have x equals 0, y equals x plus 1, y equals 7, and we'll run this again, and then x equals 42. So if I print y, I get this warning, right? Because y is stale, it depends on a previous value of x. In this case, I could rerun either the y equals 7 cell or the y equals x plus 1 cell. And And so we really, since there are oftentimes multiple choices for what to run to refresh things, we wanted to leave the user in control and preserve existing notebook semantics as closely as possible.
And I'm guessing users do that sort of thing because they want to have
Yes.
these, they use it like a stateful button sort of thing. Like I have these different states, I want to try different ones, and I realize they conflict.
I think determining that determining that would require a full user study. I can at least say that for myself, this is how I use notebooks.
Okay. An existence proof.
All right. Sure, exactly.
Raleigh, Jeffrey, do you have anything you want to say about that, or otherwise we'll go to Raleigh. All right, cool. Raleigh, I think you have a question. You're muted, sorry. Yeah.
Okay, sorry about that. Yeah, thanks a lot, Stephen. Really enjoyed the talk. So my question is about your plugin, which you described as a kind of replacement for the Python 3 kernel. So I'm wondering what happens if in that user code they call out to a kind of Python library. Are you going to be able to instrument that, or is it only if that Python library is written in Python?
Oh, that's a good question. So if you mean like for other modules that users are installing. Okay, so because I'm going to present a simplification of the state of the world, which is that we only need to worry about staleness issues between variables defined in the global scope of the notebook itself. Okay. If we use some libraries, we don't need to trace the library code. This isn't 100% true because there are things like there's that cell magic. What is it called? I'm blanking on it. The one auto reload. Yeah. There's this thing that will actually let you import your own files. And if you do that and then change those files, it will automatically reload symbols that are defined in those files. NBSafety doesn't work with this yet. We would like to make it work with this at some point, but that is going to be tricky to get correct. So we're still thinking about it. But for non-auto reload case, we don't need to worry about other library code.
So when you say within the same notebook, do you mean including kind of fields of arrays as well?
Yeah, we that's why I called these symbols actually instead of variables. I wasn't sure what the best way to refer to that is. So if I have like, oops, let's go ahead and import NumPy, and it tells me even from the import I can do that. Y equals x sub 0 plus 5, print y, and then x sub 2 equals 3. So this shouldn't show y as being stale after I mutate this entry of x. But if I mutate x sub 1, then because y has a dependency on x sub 1, it should show y as being stale. So things like subscripts and attributes are also given lineage metadata in NBSafety.
Thank you.
Sure.